In this segment, we're going to look at Kepler's three laws. Kepler's first law tells us that the orbits of planets around the Sun have elliptical shapes, with the Sun located at one focus. If a circular shape is a circle, then an elliptical shape is an oval. So how can you easily draw an elliptical shape? Well, let's say we have a piece of paper tacked to a board, and the gray rectangle is your paper that is tacked to the board. We're going to add on to it two tacks. So these hats with pins are going to be your tacks. So your paper is tacked to the board with these red pins. And now let's say you have a pencil, and its pencil point is on the paper, and let's say you have a string, and you tie the string around the two tacks and around your pencil point. So put a little bow in your string here. So with the tension in your string, you go all the way around the two tacks as far as you can, and the shape you trace out is called an ellipse. And where the two red points, the pins are located, are called focus points. So Kepler's first law says the orbits of the planets around the Sun are in the shape of ellipses. So if I drew the Sun in, and then I drew in a typical planet's orbit, it would make this elliptical shape. And the Sun is located at one of the focus points that I have drawn with a dot. And in this case, I drew the Earth in the color blue, and it is orbiting in the counterclockwise direction, or CCW. All planets orbit in the counterclockwise direction, in the shape of an ellipse. Let's look at Kepler's second law. Kepler's second law says that an imaginary line drawn from a planet to the Sun sweeps out equal areas in equal times. So let's look at Kepler's first law. We have a planet like the Earth orbiting in the counterclockwise direction around the Sun. And the Sun is located at one focus point. And the shape of the orbit is an ellipse. So let's start with the first part, an imaginary line drawn from a planet to the Sun of Kepler's second law. So let's draw an imaginary line in. Now let's look at this next part. It sweeps out equal areas in equal time intervals. So let's say we have a clock and we start watching the Sun at time t equal to 0, and it's going to orbit in the counterclockwise direction. It's going to go this far, and we're going to pause it. And we're going to call that time interval t blue. So what do we mean by equal area? Well, first of all, we need to draw in the area. So if we color it blue, and then we're going to label it area blue. So we have this triangle-looking-ish shape, and that area is the color blue, and so we have area blue labeled here. Now we're going to let the Earth continue in its orbit and take a look at it here, starting here. And now I'm going to label my line green, and we're going to watch this Earth sweep out an equal area. And we'll call this area A green, or area for green. And the interval it went through is t green. So the time it took for the Earth to go this far is t blue, and the time that the Earth took to go this far in its orbit is t green. And the areas that it swept out are A blue and A green. Now let's look at it at a different time. So let's let the Earth continue in its orbit to about a time of here. Let's pick it up there. This time I'm going to draw my imaginary line as red, and we want to sweep out an equal time interval and an equal area. And I will color this one red, and we will call it T red and A red for area red and time red. So what Kepler's second law is telling us is that T red is equal to T blue, which is equal to T green. The amount of time it took for the planet to traverse the blue part of the orbit is the same amount of time as the planet took to traverse the green part of the orbit, which is the same amount of time that the planet took to traverse the red part of the orbit. Similarly, A red, or the red area, is equal to the blue area, which is equal to the green area. And so Now we have Kepler's second law. An imaginary line drawn from a planet to the sun sweeps out equal areas in equal time intervals. So let's say the hypothetical time is equal to 2 months. We're looking at 2-month intervals. And so the amount of time, 2 months here, that we took to traverse the blue part of the orbit is the same 2 months it took the green part of the orbit, which is the same 2 months it took to traverse the red part of the orbit. But why are the lengths different? The red line, a red part of the curve, is much shorter than the blue part of the curve, which is much shorter than the green part of the curve. And that's because the areas are the same. So the red area is the same thing as the blue area, which is the same thing as the green area. So what does that mean? So what this means is, for second law, is we're looking at the speed of the planet in its orbit. So as the planet is approaching, when the sun is physically closer to the orbit, it is going to go fast around the sun. And then when the sun approaches furthest away in its orbit, it's going to go really slow in the orbit. So once again, you're looking at a fast orbit to a slow orbit. Then it picks up in speed and it goes fast and then slows down. Then it picks up in speed and goes fast and then slows down. Since the areas are the same, then, and the lengths of the green line is longer than the blue line, which is much longer than the red line, then you have to get a green line, this line that's really long, to go have that length in the same amount of time. You have to go really, really fast at that end. And to have the shortest line or curve furthest away from the sun, and the areas be the same, that means you have to go really slow furthest from the sun. So Kepler's second law is all about the speed of the planet around the orbit. Let's go look at Kepler's third law. Kepler's third law tells us that the square of a planet's orbital period is proportional to the cube of its average distance from the sun. Let's first look at the words orbital period. Orbital period is the time a planet takes to orbit its star one time. So let's say we take a look at the planet Earth, and there is the sun, and so the planet Earth is going to orbit one time around the sun in a time equal to 1 year. So then the orbital period is equal to 1 year. And we give the letter P for orbital period. And in this case for the Earth, it is 1 year. So now let's go look at average distance. So we take a look at the distance that the planet is from the sun as it orbits, and then we find the average distance. And so that average distance is going to be given the letter A. So P is the planet's orbital period, and A is the average distance from its star. And thus, Kepler's third law says the square of the planet's orbital period, or P squared, is equal to, or proportional to, so I'll draw a little fish symbol for proportional to, the average distance from the sun, and that says the cube, so that would be a 3. Now in its original form, Kepler said P squared is equal to A cubed. And so that's how we're going to leave it. P squared is equal to A cubed is Kepler's third law. Now we can make this easier to look at. P squared is just P times P, and then A cubed is just A times A times A, 3 A's. Now P has to be expressed in the units of years, and A has to be expressed in the units of astronomical units. You cannot use any other units in this equation. Let's look at an example. If Earth is about 1 astronomical unit on average from the sun each year, find the orbital period of Earth, P. Well, we know that the Kepler's third law tells us that P times P is equal to A times A times A, and I'll use dots for multiplication symbols, and that's P squared is equal to A cubed, and we're given A is equal to 1 AU, so we know that P times P is equal to 1 AU times 1 AU times 1 AU, where I'm now using parentheses, and I've dropped the dots in between. Well, we multiply this out. 1 times 1 times 1 is equal to 1. And we carry the p down, so we have a p times a p. And then we have, we want to take the square root of both sides. So we have a p on the left side, and the square root of 1 is 1. And we know the units has to be, for p, has to be in years. So we know the unit is year. And this makes sense. The orbital period of Earth we know is 1 year. So therefore, p should be equal to 1 year. And that helps us understand Kepler's third law. Let's look at Mars. So if Mars is on average 1.52 AU from the Sun as it orbits around the Sun for a typical year, what is the orbital period of Mars? So we start with Kepler's third law, p squared is equal to a cubed, where p has to be in the units of years and a has to be in the units of AU. So we know that p times p is equal to 1.52 times 1.52 times 1.52, or 3.51. And then we take the square root of both sides. And if you're going to be using your Google calculator, get out your Google calculator and type in 3.51 into your box. Then look for the square root key and take the square root of the number and hit equal. So hit square root, then equal. And you should see 1.87 in your box, so of your calculator. If we go back, we know that this would then be equal to 1.87 years. And so the period of Mars, the time it takes to go around the Sun one time, is about 1.87 years. Let's look at a third example. Let's say we're given the period of a planet is 29.5 years. We want to know how far it is from the Sun on average in its average going around the Sun, the average distance from the Sun to this planet, or the letter A. Once again, we still use Kepler's third law, p squared is equal to a cubed, or p times p is equal to a times a times a. And in this case, we're given p, so let's put that in there. 29.5 times 29.5 is equal to a times a times a. So if you multiply that out, you get 870.25, and that is equal to a cubed, or a times a times a. Now how do we solve this? Well, we have to take both sides of the equation to the 1/3 power. So then a cubed multiplied to the 1/3 power, you multiply the 3 times 1/3, you would get a to the 1, which is just a. Now how do we handle 870.25 to the 1/3 power? Let's go back to our calculator. Plug 870.25 into your calculator and look for the x to the y key. Click on the x to the y key. You will see a little box open up. In the box, hit parentheses, this left parentheses, 1, the number 1, then the divide by symbol, so there's the divide by symbol, the 3, and then the close parentheses. So once again, it's the x to the y key, followed by the left parentheses, 1 divided by 3, close parentheses. Then finally hit the equal key. It should look something like this, 870.25 to the 1/3 power before you hit the equal key. And then after you hit the equal key, you should see 9.55, and here I already rounded. So let's add this answer in. And the unit is AU, so the average distance of the planet to the star is 9.55 AU. And this object, when you look in your appendices in Appendix A, you'll see that it is the planet Saturn.